Hello, everyone. We are presenting our work on the application of graph neural networks to solve the traveling salesman problem. In the traveling salesman problem, we seek to find the shortest possible route that visits every node in the graph exactly once and returns to the initial node without repeating any edges. The visualization on the left shows the solution for a TSP of 100 nodes. The problem is straightforward to define, but difficult to solve efficiently for very large graphs. Since TSP is an abstract representation of many observable phenomena, this has posed challenges in various areas of scientific research. To approach solving TSP, we explored various graph neural network methods proposed in recent work, and chose two promising approaches to investigate. These include the graph convolutional network and the deep policy dynamic programming approach. The dataset consists of 1 million fully connected graphs with solutions identified by Concord, which is an exact solver, and each graph has 100 nodes and lies in a two-dimensional space from 0 to 1. We applied the graph neural network approaches to this data set and compared our results with the optimal solution and greedy search, which is a naive heuristic approach. One of the simplest strategies to solve TSP is a greedy search, but it often fails to find the optimal or near optimal solutions because it only considers locally optimal decisions rather than finding the global optimum. While the optimal solvers are time-consuming for large inputs, the heuristic-based solvers trade off optimality for a lower time complexity. However, heuristic solvers often require time-consuming hand tuning. So to automate this process, we'll explore the potential of graph neural networks. The input is a random set of nodes, and the corresponding labels are generated by the exact solver. We pre-process the data into an adjacency matrix and distance matrix for each set of input nodes. During the post-processing, we perform beam search on the predicted edge weight matrix to find the optimal tour. So given a graph instance, we would like to generate a closed tour of minimum length. In other words, we want to minimize the total distance traveled by providing an ordered list of nodes to travel to. The distance between any two nodes is calculated by the Euclidean distance metric and is accumulated for each edge in the solution. We take a comparative view and sample the most popular neural architectures for TSP as baselines and compare their results. Additionally, we compare our results to the highly optimized commercial solvers like Concord and nearest neighbor solution for reference. In the first approach, we tried a graph attention network with reinforcement learning. This is an autoregressive approach, meaning that at every time step, the next location to visit is conditioned on the current partial solution. The next approach uses a graph convolutional network, and that produces a heat map over all edges as shown in the figure. Edges that are more likely to be a part of the optimal tour have a higher heat, and therefore a higher opacity in this figure. And in practice, a threshold hyperparameter is used as a cutoff mask for the final edges to consider. Then a beam search is applied to produce a valid TSP tour. We found that a natural way to extend this work would be to use a technique called deep policy dynamic programming over the heat map produced by the graph convolutional network. The essence of this technique applies a beam search over the dynamic programming space instead of the full space. So in this figure, the partial tour given on the left will always be better than the one on the right. So the right will never be part of an optimal solution. When the input is a heat map, at each iteration, the beam search will expand and prune the dominated solutions, improving the quality of the beam search. The beam width allows for a tunable trade-off between computation and performance, and the neural network needs only to be evaluated once to produce a heat map from which DP-DP will operate on. For a single instance, we show that the tour found by each method. The blue points represent the nodes, and the black arrows represent the directed edges in the optimal tour. For the deep learning-based approaches, we show a heat map indicated by the red lines connecting the nodes, and we found that both deep learning approaches outperformed the greedy search, and DP-DP converged to a comparably optimal route as reported by Concord. Here we show the mean distance and optimality gap of optimal tours found by Concord, greedy search, Joshi et al., and DP-DP methods with a beam search of 10K. The deep learning-based approaches offer significant improvements over the naive greedy approach. DP-DP in particular has a very small optimality gap relative to the exact solution. So in our study, we found that leveraging state-of-the-art neural approaches in conjunction with classical algorithms can offer competitive alternatives to the state-of-the-art solvers. These TSP approaches have various applications outside of theoretical computer science, including efficient genome assembly, traffic predictions, and de novo drug discovery. Thank you.